Good morning, everyone. Welcome to the EasyPower Tuesday Refresher Series. My name is Jim Chastain. I'm an applications engineer here at EasyPower. I want to welcome you to this pre-recorded presentation. As such, we won't be able to answer questions real time, but please, during the presentation, utilize the question box if you would so desire, and we'll be able to follow up as the opportunity presents itself. So first of all, I want to apologize for the title. These are really not tricks or hacks to the tools. These are well-documented features, and the intent is to help you improve your productivity and decrease the learning curve time to utilize the tools. So with that, we put a lot of emphasis on understanding the mechanics and determining where missing data occurs in your data collection process, to help avoid making multiple trips back to the site during the initial stages of creating a one-line. And then once we get into a model that's relatively clean of errors, there's checks that we can do to make sure we're not missing data or looking at the setup in the incorrect way. One of the things I strongly recommend, at least in the early stages of learning EasyPower, is to start small with your one-line design. Have one each of a utility, maybe a generator if you have that in your system, and one load, and then the connections between that utility source and the load, covering as many voltage changes or as different types of protective devices. The point being that once you get the one line drawn, can you produce the results you want, and in particular the labels? Because if you can't do it on a very simple one-line diagram, you're going to have a real problem when it gets to the larger one. So rather than jump into something where you're drawing a one-line this complex, make sure you can do an analysis on a very simplified, and the data is less important as far as the accuracy and more important understanding which data is going to be affecting your calculations. Once you're there, once you've gone through this stage and you appreciate the mechanics of the tool, then by all means, do your data collection. And as you do the rolling collection through your system, try to do the modeling and make sure you understand each of the elements that you're encountering, have complete data. Once we've got our one line drawn, then the next question is, do we have any missing data? And the tool to utilize at that point is called the database browser. Frequently, I get dozens of one-line diagrams, one-line files from new customers, and we walk through them in a process we call a power start. And one of the first things I do is illustrate the use of the database browser to look for equipment that may be missing data or incorrectly applied. So this is what that looks like. Once I've got the one line created, come up to File, Database over here on the left, Database Browser. And this shows me the generic listing of all the generic types of elements I have in my system, and then the total number of buses. In this case, it looks like there's 93 buses. And I can inspect each category by using the pull down under the equipment arrow. Let's look at the buses first. What I'm looking for is this column called bus bracing. When we calculate equipment duty, where we compare the maximum fault current that's going to occur at any bus against its capabilities, this is the number we're searching for and comparing against. So the question is, why are we not including numbers for these buses? There may be a valid reason, there may not be, but I'm just saying we want it to be a conscious decision as far as what we're generating. Next, I like to look at the cables. And again, what I'm looking for is things that seem out of the norm. And in this case, I've added a cable here at the very top. And the thing that looks out of the norm is the ampacity rating of 10 amps, which is the default value. And so that indicates there's some problem with the setup of this cable. If I double click on the yellow control box, it brings up the dialog box for this particular cable. Looks like things were set up okay, except I notice over here on the raceway we've selected none. that is an issue with the way the calculations are done in EasyPower. And so I need to designate the type of raceway and the material, and by so doing, I get the proper ampacity rating and size for the size. So by adjusting that or making that improvement, I get the ampacity rating accordingly. Next thing I like to look at are timing devices, which are hugely important for arc flash calculations. And again, what I'm looking for are the either a manufacturer is not listed in the setup, or the short circuit rating is not showing on the data sheet or on the spreadsheet, which indicates I haven't connected this particular part number with its data sheet in the device library. So let's look at one of these and see what's going on. On this first one, sure enough, I haven't set it up at all. So that's something I need to deal with. And on this third one, let's look at, it looks like its part number is set up and everything is fine, except it's not showing an interrupt rating. And when I click calculate, it still isn't showing an interrupt rating, which tells me this part number doesn't exist in the device library. So with that, I want to go contact tech support, said, hey, am I using a part that's not in the device library for some reason? And let me try another one. So what we're looking for, let's look at this one that it looks like it's set up. It's showing 0 on my part number. So yes, this is all set up correctly. It looks like we have the details here, but there's not a short circuit rating. When I click calculate, the number changes to 85. So this step of having to click calculate to ensure that it's in the device library, it's not been done for that particular part. So that's something that needs to be corrected. So I have two issues. One is the part number wasn't set up. One that was set up, I didn't click calculate to make sure it was in the device library. And then it appears there's some issue with the device library that doesn't have this particular part number included in the ratings. Now, we've actually checked into this, and what the issue is that the data that's in there shows that this is an IEC type of device, and consequently it won't have a breaker rating for that particular device for ANSI calculations. So again, that's being addressed. But at any rate, I've kind of confirmed that's a holdup with my project. And then the same thing for fuses. And again, what I'm looking for is interrupt rating. I see several down here with 0 on it. If I go check on one of those, let's see what happens. Looks like we have a part number set up. I want to see one or both of these numbers change. The fact that this changed to a 0.9 interrupt rating means that the calculate button wasn't engaged. Okay, so that's the database browser, and what we're looking for is missing data. Now, once we've got our database cleaned up, the next step is going to be doing short circuit analysis. So as we've seen, as I go to short circuit focus, anything with a minimum minimum of data will be highlighted, but are we going to get the correct results as far as equipment duty? Let's kind of go back and look at this. If I close my database browser, go into short circuit focus, we get a clean one-line diagram. And now I'm going to do equipment duty. So I take a half cycle current, 3-phase volted fault. Let's just do a single bus just to eliminate the time involved. Let's pick this bus, fault it, and then look at equipment duty. So by faulting this is going to show me the current on this particular bus if it has a 3-phase volted fault. And what I see is I see 28,000 some odd amps coming from upstream and nothing because we have no loads downstream. And the question is, will that 28,000 exceed the rating for the bus or the elements on there. Now these are the answers yes. Specifically, we're dealing with the fact that that part number wasn't in the device library. So that's why there's a red indication with no numbers on there. Let's pick this, go to one that has a better chance of. So what I'm looking at is these numbers, and a positive number means that it's being overrated. And if I come back and look at my short circuit reports and create an equipment duty report for a violation that parts have been violating, I can see under my list of windows, my equipment duty report, that these are all rated for 65,000 amps, and I'm showing 119,000 as the worst case fault current. Well, as I go back and look at my one-line diagram, I can tell I have some cross connects that are engaged. I have generators online that would make a big difference, and we may want to start considering having scenarios where we only have certain tie breakers closed. If we have any situation where we have multiple devices enclosed, then we have a serious problem, and that's something we need to deal with. We notice also the case with the ATSs, and so my guess is somewhere along the way, if we go back to database edit, we will have a number of dialogue, a number of scenarios defined. Let's just see if they've set them up. So no, so that would be a recommendation, is that we need to set up scenarios reflecting configuration that would be consistent with the normal loading on a system, and then look for the worst case situation. Okay, so far we've verified we have some equipment duty issues. We have now the equipment duty is set up under short circuit options, control. Down here on the lower third of this block, the equipment duty is set up as a threshold, and normally we use a negative 10%, which basically says I'm anticipating adding more capacity to this bus or more loads on this bus, which will increase the short circuit current contribution if I have motors. And so I need to just tell me if anything's within 10% of its rating. And so where numbers are negative, that means they're still compliant, but they're within that threshold. Where they're not showing up at all, that means they're not being inside that threshold, and they should be safe. So that's under equipment duty threshold. So far we've found an issue with our device library, missing elements data, and some threshold issues. Now let's go into short circuit. Now that we're happy with short circuit, we've corrected the errors there, we want to check coordination. And so that it's not necessary to do complete coordination study in every arc flash assessment. It is necessary to check on equipment coordination, and this probably is most easily done with a feature called the sequence of events. And this is a very vital tool. And one thing I want to verify or understand is that frequently people will use the 2-second rule as an initial setting, and I discourage that because it can obscure coordination issues if we have a problem. And so before I just automatically start applying a 2-second limit on calculations, I want to look at the verification of the 2-second of the coordination model. So let's look at system here where we've completed the one-line diagram. We're happy with the short circuit results. I'm going to go into coordination and pick a single downstream load or bus. I want to look at half cycle current, three-phase bolted fault, and fault that single bus. Now, that gives me access to this little icon on the second row called sequence of events. And by invoking that, it shows me the chronological tripping order of every upstream breaker or protective device from that between this fault and the energy source. So if this bus faults, this breaker will trip in 190 milliseconds. This breaker will trip in 35 seconds. This fuse will trip in 32 seconds. And this relay will trip in 300 milliseconds. And these are flagged red because they're out of order. You might say, well, that's interesting stuff, Jim. Can you show me a report? If we come up to PDC options, bottom right-hand column under the General tab, select Create Sequence of Events Reports, and go back and fault that single bus again. Now, in addition to the display on the one line, we have under our list of windows a sequence of events report that shows us that in tabular form and indicates that we more than likely have some miscoordination going on. And so the question comes up, can I do the whole system at once? Well, by selecting all the, or at least in this case, both feeders, both sides of the main, I can fault the bus. But as far as the display of sequence of events, there's too much data to be able to show the results on each bus. But look what happens when I look at the sequence of events report. It shows me literally every bus and then the upstream tripping order of every protected device between that bus and the energy source. So this is not the way you do coordination, but this is not a bad way to check coordination. And at the very least, it lets me know whether I need to spend a lot of time and how much of an effect we may have on the results if we do a more complete coordination study. Now, I mentioned that using the 2-second rule prematurely can obscure coordination issues. So let me kind of jump shift into a more detailed problem where the customer was having issues trying to sort out the tripping parameters and the arc flash calculations as a result. And part of it was due to the fact that he prematurely addressed the 2-second rule. So the report was, we're getting elevated arc flash calculations on this particular bus. And it looks like it's a 480 volt bus, and there's several different breakers and some upstream sourcing from 13.8 kV. If we go to short circuit and fault this single bus, we can see that the calculations give us 42,000 amps from above, 52 amps, 770 amps, and 116 amps from below from apparently the loads. And if we look at instant energy, sure enough, we get very high or disconcerting instant energy. So part of the problem is, what are we doing for coordination? So let's go back and look at setup. In our setup options on our arc flash hazard tab, we've already got the time limit for 2 seconds. We've got instant energy calculated using momentary current, and we're requesting a detailed output. So this is kind of like mixing our messages here. First of all, we want to use the standard of 1584 suggests using a dynamic assessment of arcing current. In EasyPower, that's called integrated method. And if we're using, and it also suggests that we exclude the main for calculations. So let's see if making those adjustments make anything change. Well, it doesn't change this. This still seems out of whack. If we look at our current, the thing that strikes me is this is a very low current, and it could be contributing more instant energy calculation because it's not tripping anything. So let's kind of go back to the arc flash calculations and disable this breaker. And it doesn't seem to change. Just disable this breaker. Now with this breaker open, we have 2 calorie exposure. And if we arrange for arc flash, we see that we have a manual time indicated, which is our 2-second limit, is indicated by the arc time. And it's also saying we have an out of range concern on the resulting calculations. So I suspect this is a function of our short circuit current being relatively low and not causing a trip. So let's kind of go back and see how setup is for this particular bus. So if we look at the bus setup, we know now here's another issue. We're asking for both include and exclude. The customer said, no, this is definitely an including. There's a barrier there, so we can include the main on this bus. And we can go back and see if that makes a difference. And if we look at instant energy, it does make a difference. And now this is where I'd like to go back and see, well, what's really causing the problem. So by expanding our 2-second limit at 480 volts, we see that in fact it is the issue where we have very low current and it doesn't trip for the maximum 2-second limit. And it's a result of that one load. So this goes back to my discussion about, well, maybe we need to have an understanding of where this current is coming from and does it really make sense. And it turns out in this particular case, it's from a bypass around a UPS. And so it may not be something that's realistic as far as normal operations. But at the same time, what's going on up here is, and the original report was maintenance mode isn't working. If I turn maintenance mode on, in fact, it works quite nicely as long as I don't have this breaker engaged. So the result is maintenance mode works great. The scenario needs to consider whether or not this is a realistic load in normal operations. And I need to reflect on how I'm going to control my setup, including the 2-second rule. Okay, so that seemed to solve that particular problem. And we didn't need to use, actually we could have used sequence of events and it would have shown that we were having a long delay time because of that low current. Okay, so we talked about control options, arrange for arc flash display. Another concern is, when does manual time indicate, where does it come from when we're using Lie equations? And we've seen one case where manual time was indicated when the 2-second rule was being used. It also would be an indication where we're exceeding the time limit of 1,000 seconds, and it would indicate a manual time. But what does it mean when we're utilizing Ralph Lie as an alternative because we're outside the scope of the 15K limit on 1584? Well, let's pull up another example. So in this example, we're looking at instant energy on a 34K bus, and we're getting results, half cycle current of 8,000 amps coming from upstream, 260 amps coming from contribution downstream. And we're seeing, when we calculate instant energy, that it's tripping on manual time. Well, and it's also indicating out of range on the comment section. We go into, let's go back into our PowerPoint for a second. If we look at NFPA 70E under the Annex D, where it talks about Ralph-Lee equations calculation method. It describes clearing time as based upon the model is based upon max bolt-to-fault current, and it describes ways to estimate the clearing time can be used in the calculation. It suggests that if we're in the current limiting range for a current limiting fuse, then the time limit could be specified at 4 milliseconds. Whereas if we're using a 15K circuit breaker, clearing time might be 6 cycles, and that would result in an opening time of 2 cycles for the breaker itself, the relay operating time of 1.74 cycles, and then add a safety margin of 2 cycles to give us a total of 6 cycles for that instantaneous setting. So let's kind of go back and see what we have set up in this particular example. If we look at the arc flash settings under advanced, we can see we've selected if the voltage exceeds the IEEE maximum, which is 15K, and it does in this case, we're selecting Ralph-Lee method. So that brings us back to what are we using for calculations for the time, estimate. Well, based upon the way this is set up, here's a arc flash relay that's checking on the differential current, so it's a differential relay looking at the incoming and outgoing. And the estimate of time is a function or is something that's entered on the downstream bus or the bus that's being protected. If we look at arc flash, we see that we're depending upon user-defined time of 0.026 seconds. Well, if you look at the data sheet for a SEL 787, that's the response time of the relay itself. And although we set this up properly to show that we're going to be activating one or both of these two high voltage breakers, because this is not a function we can simulate, that time needs to include the time that we set up of 0.02 seconds, of 0.026 seconds. It does not include the opening time of the breaker itself. So when we calculate this time, it's not just the relay response, but it's also the opening time of the breaker. So in realistic terms, this should be at least another 2 cycles, and that needs to be documented in our estimate. Now, the point I'm trying to make is if we were going to set this up as an overcurrent relay, as we would up here, when I go back to my database edit and look at the way this breaker's set up, it's being addressed to activate a high voltage breaker accordingly, and the breaker itself has a function or an opening time that's designated of 5 cycles. And so the delay time and the delay of the current response will include that opening time. So when it comes time to use a designated user-defined time, we need to ensure that that time is included in our estimate here. And more than likely, we would want to include user-defined time as well as the TCC trips, so that if we have a downstream fault current, this would show the response to that as well. So anyway, what I'm looking at here is the setup time for use of the Ralph-Lee equations and the results by faulting this bus and looking at the so now this is using the upstream bus, and what am I using for current? We'd use momentary current because it's not going to be a long trip. And by so doing, we show the response time both for the overcurrent and the arc flash relay. Okay, again, that would be a scenario situation, but the use of the range for arc flash is showing us the need for that. So anyway, that's been described. And so that number, whatever our estimated clearing time is for the arc, can be utilized in even using the Ralph-Lee equations where we've exceeded 1584. Okay, stomped all over that one. Hopefully it made sense. I would like to remind folks that we have additional resources from EasyPower. For all new customers, we have a Power Start, no cost available tool orientation. And as long as your maintenance is current, it's also available to new employees of tool owners where you would want to help bootstrap the new engineers to use the tools in your system. So the question is it time for a Power Start? Thank you for attending today, and we look forward to seeing you online at a later date. Don't forget to check the newsletter to see what the new scheduled webinars will include. Have a good day.